Hey everyone, another day, another DSA concept. So today we're going to be looking at Kahn's algorithm, which is used for topological sort. So let's just look at the definition and then we'll go from there. Okay, so it states that topological sort is a linear ordering of vertices such that for every directed edge between U and V, from U to V, U appears before V. Okay, so let's look at this example that I've kind of drawn out over here, and we'll look at the first layer. So we have 5, and we see 5 is over here, and then we see the layer after that, we have 1 and 4, so we have 1 and 4, and then those are pointing to 2, so we have 2, and then 2 is pointing to 3, so we have 3. So if we look at 2 over here and consider this to be node U and then 3 to be node V, we see that there is a directed edge going from U to V, and even in our topological sort, we have U before V. So that's basically what it means, like the order in which it's going with correspondence to these directions that they're headed towards. Okay, so there are 2 conditions over here for Kahn's algorithm, not conditions, actually there's just 2 points. So it works on directed acyclic graphs, okay? So direction is important here. And if we have an undirected graph, we can't use Kahn's algorithm. Maybe for traversal, we can use a DFS, but this is not gonna work. And we're using Indegree of nodes. Okay, so I think the term itself is very intuitive, but let's just go ahead and see. So if I have a node 1 and I have 0, which is heading towards 1, the Indegree of 1 becomes 1. Now if I have another node which was also pointing towards 1, its Indegree would have become 2. And if I have a node that's going from 1, the out degree of 1 is 1 right now. So yeah, that's basically, I mean, in degree, out degree. I think that's understandable. Okay, so these are the steps that we follow for Kahn's algorithm. I'll just read it out once and then we'll go ahead with an example so it'll kind of stick. So the first thing we do is we pre-compute this Indegree for all of our nodes. Then we're going to push all the nodes with Indegree 0. So basically those are the origin nodes that have nothing heading towards them and everything starts from them, or they're a single node or something. So we're going to push those nodes with Indegree 0 into a queue. We're going to pop a node from the queue. We're going to add that node to our topological order list, or however we're saving it. And then once we remove a node, we're going to also decrease the Indegree count of the nodes that were connected to this node. So we'll see that in the example. And after that, if we have another node or a few nodes which are now having an Indegree of 0, we add those to the queue and we repeat this process until all our nodes in our entire queue is completed. So there's also a way that we can use Kahn's algorithm to check if we have cycles, and that is like if the output, at least our visited set or the topological order list, if the length of that is not equal to the length of total nodes, then we know that we have a cycle. So we can see that over here. So if I look at 1 initially, let's say I'd put 1 to the queue, and yeah, so let's say I removed 1 because it's an Indegree of 0, and that removes an edge over here, which makes the Indegree of 2, well, the Indegree of 2 decreases by 1. So after that, I see the Indegree of 2 is still 1 because there's an edge coming over here. But if I look at the nodes, the Indegree of 2 is 1, the Indegree of 3 is 1, and the Indegree of 4 is also 1. So after I pop the node 1 from the queue, and I still decrement the Indegree counts of the nodes connected to it, I don't get any node which has an Indegree of 0. So basically my entire process would stop there, and my visited set or my list would have only 1 node, when in actuality I have 4 nodes. So that tells me that somewhere there is a cycle. Yeah, that's how it's used. And the complexity is V plus E because we're popping out all these nodes and then we're traversing through the neighbors of each node and decreasing its Indegree count. So that's V for the number of vertices and E for the number of edges. So that's V plus E. And then the space complexity for our queue would be O of V because number of nodes. Yeah, so as I mentioned, we'll go through an example so that we can remember things better. And let me do one thing. So over here to the side, I am going to keep an I'm going to keep a mapping over here of in degree. And as you can see, to the nodes that I have, we have a total of 5 nodes. So we have 0, 1, 2, 3, 4, and 5. And we'll map their in degrees. What else do we need? So we need a queue, store the nodes that we're having. And then we can have something like a tuple order list, so we can use that as like our output if we need to hold order. Okay, let's just draw this out. So it says we have a node 0, which is connecting to a node 1, okay? And then we have 0 also connecting to node 2. So now I need to maintain in degree, right? So in degree of 1 is now 1, and in degree of 2 is also 1. And then 1 connects to 2. So in degree of 2 is incremented by 1, so it becomes 2. Then we have 1 connecting to 3. So in degree of 3 is equal to 1 now. 2 also connects to 3, so this gets incremented to 2. 2 to 4. Okay, so 4's in degree becomes 1. 3 also connects to 4. So this is incremented again, and then 3 connects to something like 5. This becomes 1, and then 4 also connects to 5, so this becomes 2 again. Okay, so we'll see. Okay, let me just, to make it more readable, we'll just write those. So 0 has an in degree of 0, 1 has an in degree of 1, and everything else has an in degree of 2. Okay. So now maybe I'll use a different color. We can start our Kahn's algorithm. Let's start our sort of BFS traversal over here. And the first thing I have in my queue, because it has an in degree of 0, is the node 0. All right. So I'm going to pop this out. I'm going to add that to my topological order. So I have a 0 over here. And once I remove the node 0, I'm going to look at the neighbors who have been affected, right? So 1 is affected and then 2 is affected. So I'm going to go and decrease the in degree count of 1, node 1, by 1. So it becomes 0 over here. So then once it becomes 0, I add that to my queue. And I also see that 2 is also affected, so the in degree count of 2 also decreases, so now it becomes 1. All right, so now in my queue I have 1, and once I pop 1, I add it to my topological order over here, and then I see once the node 1 is removed, it's affecting 3 and 2. So 2's in degree becomes 0, and once that happens, 2 is going to be added over here. And then 3's in degree count is also decreased, so that becomes 1 now. Yeah, that's correct. Okay, so now what's going to happen, I'm going to pop out 2. I'm going to add that over here. I'm going to look at the nodes connected to 2. So that's 3 and 4. So I'm going to decrease the in degree count of 3 now, which is going to become 0. I'll add 3 over here. And the in degree count of 4 is also decreased, so that becomes 1. Okay. And now I pop 3 out. And once I pop 3 out, let's see, what does it affect? So that's going to affect 4 and 5. 4 becomes 0, and 5 becomes 1 over here. 3 is added here. 4 is added to my queue because now it has an in degree of 0. So once I pop out 4, what happens is I add that to my topological order, and the in degree of 5 becomes 0. Then 5 is added to the queue, and once I pop out 5, it doesn't really affect anything because it's the last node that's actually left. And once I pop that out, I add that over here. So this becomes my topological order, which is actually what we were looking for. So yeah, that's correct. And so let's see, we didn't really have any cycles over here, but just to make sure, we're going to see is the count of this actually equal to the number of nodes that we were given. And so the number of nodes that we had was also equal to 6, and the size of this is also equal to 6. So yeah, Kahn's algorithm has run successfully. We got our topological order, and we also verified that there were no cycles. So yeah, we'll look at a few problems after this in the next videos, and I think that will help you understand of how you can actually use this to solve your problems. But yeah, so anyway, thanks everybody, and happy coding.